Section: Introduction. In this section, we delve into the exploration of a solution that benefits both language and mathematical abilities for practical deployment of large language models, LLMs. Instead of focusing on the supervised fine-tuning stage, we emphasize enhancing ILM's mathematical skills during the feedback learning phase in LLM alignment. Unlike the traditional approach of reinforcement learning from human feedback, we introduce a math critique model derived from the LLM itself to provide feedback on its generated solutions. This means we reinforce LLMs based on AI feedback on mathematical accuracy. Our approach consists of two stages. 1. Rejective fine-tuning, RFT. This process involves multiple sampling iterations where certain responses are rejected based on specific criteria, and the remaining responses are used for supervised fine-tuning. We use math critique evaluations to refine the dataset, focusing on improving the LLM's ability to generate mathematically accurate and logically consistent responses. 2. Direct preference optimization, DPO. This stage updates the model directly by learning from pairs of correct and incorrect answers. Building on the RFT step, we sample multiple times for challenging problems and use math critique to select the pair of answers with the most significant difference for learning. We also introduce the MATHUSEREVAL benchmark, which evaluates LLMs on complex real-world mathematical problems. This dataset includes high school-level questions and real-world application problems to better match users' needs. Our contributions include proposing the self-critique pipeline, which enhances both mathematical and linguistic abilities simultaneously. We conduct experiments on a ChatGLM-3 to 32B LLM and achieve state-of-the-art results on various datasets. Additionally, we analyze the factors influencing the enhancement of a model's mathematical abilities and provide suggestions for future development directions. Various methods have been explored to improve ILM's mathematical problem-solving abilities, such as prompting methods, supervised fine-tuning, and reinforcement learning. Mathematical evaluation is crucial for assessing LLM capabilities, with benchmarks like GSM-8K and Math being widely used. These datasets cover a range of subjects and difficulty levels to evaluate a model's problem-solving skills accurately. Section Summary. In this section, we introduce the challenges faced in deploying large language models, LLMs, that excel in both language and mathematical tasks simultaneously. We propose the self-critique pipeline, which enhances ILM's mathematical and linguistic abilities by utilizing a math critique model for feedback during the alignment process. Through stages like rejective fine-tuning, RFT, and direct preference optimization, DPO, we aim to improve ILM's mathematical reasoning while maintaining their language capabilities, leading to state-of-the-art performance on the MATHUSEREVAL benchmark designed for real-world mathematical problem-solving evaluation. Section: Math Critique. A general critic for math. In this section, we constructed an accurate evaluation model called Math Critique. It assesses mathematical responses by scoring them based on questions, reference answers, and providing an explanatory analysis with a score between 1 and 10. Unlike traditional reward models, Math Critique uses language models' contextual abilities to make more precise judgments by incorporating reference answers. It also utilizes explanatory analysis inspired by thought chains to improve scoring accuracy and interpretability. Math Critique classifies responses into 4 categories: entirely incorrect, partially correct but with errors in the process, mostly correct but with some flaws in the process, and completely correct, corresponding to score ranges of 1 to 2, 3 to 5, 6 to 8, and 9 to 10, respectively. The model takes a question, a reference answer, and the model's answer as input and outputs a critique and a score. We use 2 evaluation methods with Math Critique: average score evaluation and hard split evaluation. The average score evaluation calculates the mean of critique scores for a set of questions, while the hard split evaluation categorizes answers as passing or failing based on a predefined correctness threshold. The overall score is determined by the proportion of correct answers out of the total questions. For data collection, we redesigned scoring rules for mathematical responses, filtered a dataset containing math questions, reference answers, and model responses, and annotated the data using ChatGLM and ORM. This process resulted in 10,000 annotated entries. We also manually annotated a portion of data entries into 4 categories and mapped them to a 10-point scale. We introduced the self-critique pipeline, a weekly supervised iterative training method to enhance mathematical abilities using math critique. This pipeline involves training a math critique model, a chat model, and iteratively fine-tuning them using rejection sampling. The final step includes using the latest math critique model to sample contrast data and proceed with DPO training. In the first stage of the pipeline, we utilized rejection sampling based on math critique to fine-tune models. We designed sampling principles to ensure diverse question sampling and selected correct responses after deduplication. This process led to the creation of the Critique RFT dataset, which includes sampled questions and responses meeting a minimum correct score threshold. Section Summary. In this section, we introduced Math Critique, a model that evaluates mathematical responses based on questions and reference answers, providing scores between 1 and 10. By categorizing responses into 4 groups and using explanatory analysis, Math Critique enhances accuracy and interpretability. We also developed the self-critique pipeline, a training method that iteratively improves mathematical abilities by supervising model training and rejection sampling, reducing manual annotation efforts and enhancing model efficiency. Section. Stage 2. Direct Preference Optimization. In this section, we utilized the Direct Preference Optimization (DPO) method to improve our model's performance after Critique RFT. The DPO method is advantageous due to its simplicity in handling data flows, stability, and speed during training. It directly compares correct and incorrect answers to the same question sampled from the model post-RFT. We included the SFT loss of DPO positive examples during training as an approximation for a regularization term. Our DPO data filtering process is similar to Critique RFT, with the main difference being how DPO training pairs are constructed. We select DPO pairs based on the most significant difference in math critique scoring results between a correct and an incorrect answer. In the Critique DPO dataset, each element is a tuple containing a sampled question, the chosen answer, and the rejected answer. The chosen answer surpasses a correct bound threshold, indicating a satisfactory level of correctness, while the rejected answer falls below a rejected bound threshold, signifying an incorrect or unsatisfactory answer. For math critique training, we start with the ChatGLM 3-32B model and refine it through SFT or Critique RFT iterations. We use specific learning rates and batch sizes for different scales. During Critique RFT training, we merge datasets from previous stages and fine-tune the model using a max log likelihood loss function. In Critique DPO training, we observed instability when using DPO loss alone, so we introduced a cross-entropy loss for the chosen answer as a regularization term. This addition aims to improve model training stability. We use the DPO dataset for training and experiment with different coefficients to optimize the model. We also introduce MATHUSEREVAL, a test set for real-use scenarios with challenging mathematical problems. The test set is divided into elementary and advanced categories with subcategories. We evaluate using GPT 41106 and math critique methods, reporting a VG score and hard split scores for each category. Section Summary. In this section, we utilize the Direct Preference Optimization (DPO) method to enhance our model's capabilities following Critique RFT. The key advantages of DPO include its simplicity in constructing data flows, stability, and speed during training. We directly compared correct and incorrect answers to the same question, sampled from the model post-RFT, and integrated SFT loss of DPO positive examples during training as a substitute for a regularization term. Section: Data collection. In this section, we will discuss our data collection process. We gathered data from various sources, including public datasets and middle school and university exam questions. For English data, we used prompts from GSM-8K and math training sets and their corresponding responses. We also utilized publicly available middle school and university exam questions, using the provided answer formats as common answers. In our research, we focused on testing the MATHUSEREVAL dataset, which combines simulated dialogue records and actual exam papers, offering a wide range of question styles. We also examined English academic datasets like GSM-8K and math, containing math problems from middle and high school levels. Similarly, we explored Chinese academic datasets such as APE 210K and C-Math, which feature questions from middle and high school levels. Additionally, we included the Hungarian national exam as an out-of-distribution test set. It's important to note that we only used the training sets of GSM-8K and math for data generation across all test sets. To evaluate our model's linguistic capabilities, we selected the Chinese component of a line bench and full MT bench for testing. We compared our model with various baselines, including open-source mathematics-specific models, open-source Chinese models, and leading proprietary models. Our evaluation metrics involved performing greedy inference once on all datasets and reporting results from different academic datasets and benchmarks. Our main results showed that our model outperformed others in various tasks, achieving high scores on different datasets. We observed significant improvements in mathematical capabilities across different datasets. In comparison to proprietary models like the GPT series by OpenAI, our model demonstrated competitive or superior performance in specific areas, showcasing strengths in mathematical reasoning and cross-linguistic generalization. We conducted ablation studies to analyze the impact of data composition on our model's performance. By integrating real-life scenario data and English data, we observed improvements in performance on respective datasets. Additionally, incorporating math-specific data enhanced our model's mathematical capabilities significantly. Our two-step approach aimed to align the model with real-world conditions, showing notable enhancements on medium difficulty questions. Furthermore, we assessed the effectiveness of math critique through empirical experiments, demonstrating its superiority over previous models in judgment accuracy. We also conducted out-of-distribution tests on the Hungarian national final exam to evaluate our model's mathematical capabilities in a completely new environment. Our results indicated promising performance, especially in Chinese language capabilities. Section Summary. In this section, we collected data from various sources including public datasets like GSM-8K and math for English questions, and middle school and university exam questions for Chinese questions. We primarily tested our model on the MATHUSEREVAL dataset, which offers a diverse range of question styles. Our model outperformed others on various academic datasets and demonstrated strong mathematical reasoning and cross-linguistic generalization capabilities, especially excelling in medium difficulty questions. Section: Limitation and Future Work. In this section, we identified some limitations in our mathematical models that we aim to address in our future work. One issue is our model's difficulty with questions involving drawings, as it is purely linguistic and struggles with tasks like accurately drawing connections between numbers. Additionally, our model faces challenges with questions that require image understanding. To tackle this, we plan to explore integrating multimodal input and output components. Another limitation we observed is in precision calculations, particularly with multiplication, division, or exponentiation involving 3 or more decimal places. Our model may deviate by up to 5% in such cases, similar to findings in GPT-4 models lacking a code interpreter. While increasing model size may help, this issue could persist for pure language models. One potential solution is to use external tools for computation or incorporate a code interpreter. However, our current focus is on improving the mathematical abilities of pure language models, and we intend to work on resolving these issues in our future research.